In recent videos for quick precalculus review, we've been using exponential functions both to model exponential growth and exponential decay. It was a population growth problem and a car depreciation problem. In both of those cases we had an initial value, and that made the algebra a little simpler. In this part 10 here, we want to do something a little bit harder. We want to try to fit an exponential function to two data points, neither of which is the initial value at time equals 0 or at x equals 0. We also want to try to symbolically represent how the resulting exponential function changes, and I'll be more specific about the meaning of that as we go on here. Before I do that, I want to start with what we ended with in the last video. We did a qualitative analysis of families of exponential functions. The expressions for the functions are these things of the form a times b to the x. When we typically think of a and b as both being positive, b positive for sure. When b is bigger than 1, that's exponential growth, and when b is between 0 and 1, that's exponential decay. I'm putting this inside a manipulate command in Mathematica that allows me to make a slider-enabled animation. I can change the values of a and b by moving the sliders, or I can play them. Take a look at it here. A is the y-intercept. It's the initial value for a times b to the x. When you plug in x equals 0, you get b to the 0 is 1, so you get an output of a. B is a little harder to understand, but it's still not too hard. For example, if b is 1.5, what that represents is that represents 50% growth for each unit increase in x. Each time x increases by 1, the y value, the output, increases by 50%. For example, when x is 0, y is 2. If I increase x by 1 unit to 1, y goes up by 50%. 50% of 2 is 1. 2 plus 1 is 3. If I increase x again by 1 unit from 1 to 2, y goes up again by 50%. 50% of 3 is 1.5. 1.5 plus 3 is 4.5. One more. If x increases from 2 to 3, y increases by 50%. 50% of 4.5 is 2.25. 2.25 plus 4.5 is 6.75. So that's what happens when b is 1.5. It's 50% growth for each unit increase of x. What if b is between 0 and 1, say 0.8? What that means is that each new value, as x increases by 1, is 80% of the old value. Said another way, y decreases by 20% each time x increases by 1%. For example, when x is 0, y is 2. 20% of 2 is 0.4. 2 minus 0.4 is 1.6. So y went down by 0.4 to 1.6. What's 20% of 1.6? It's 0.32. 1.6 minus 0.32 is 1.28. That's the y-coordinate of this point right here. That's the meaning in that situation. So I would encourage you to think about that a little bit more. That's the main thing I wanted to get across there. Let's go back to the main example for this video. It is a new example. So far we've just done examples 1 and 2. Here we have a new example 3. It's not a real life situation. We're just thinking about pure math here. We want to find the unique exponential function of the form y equals a times b to the x that goes through these 2 points that you see here, negative 2, 25/12 and 3, 648 over 125. I picked some fractions there because it makes the a and b turn out kind of nicely. Okay, so what do we have to do? We have to solve for a and b. Plug in the values of x that you have and set it equal to the corresponding values of y. That's going to give you a system of equations. The first equation is going to be that the y-coordinate of the first point, 25/12, equals f of the x-coordinate of that point, negative 2. In other words, it equals a times b to the negative 2 power. What about the second equation? 648 over 125 is the output of the function when x is 3. So 648 over 125 will equal a times b to the third power. Replace x with 3. Alright, we need to solve the system of equations in these unknowns a and b. There's a couple different ways you can do it. One thing I like to do is I like to divide one equation by the other. Take this equation and divide it by this one, say. It's the first one. So we would get, what with the numbers? We'd get fraction 648 over 125 divided by the fraction 25/12. Of course, when you divide fractions, you have to multiply by the reciprocal of the one you're dividing by. That'll equal a fraction that I get when I take a times b to the third and divide it by a times b to the negative 2 power. Now you can simplify pretty nicely. The a's cancel, they go away, you're just left with b to the third over b to the negative 2, which You should recall from your properties of exponents can be simplified to b to the 3 minus, careful, negative 2, which is b to the 5th power. What about this fraction here? Again, that's 648 over 125 times the reciprocal of the bottom, 12 25ths. Flip the numerator and denominator. We don't get cancellation here, but the numbers do end up working out pretty nice. You can check this with your calculator. 648 times 12 is 7,776, and 125 times 25 is 3125. And both of those numbers are actually perfect 5th powers. B, it turns out, when you raise this thing to the 1/5 power, turns out to be a pretty nice number. Turns out to be 6/5, or 1.2. You can check that with your calculator. Mathematica can check it as well. Raise that to the 1/5 power, get 6/5. Alternatively, 6/5 to the 5th power is this fraction. All right, so B turns out nicely. What about A? You can take either one of these equations and solve for A. For example, we can take the first equation and multiply both sides by b squared to get A equals 25 over 12 times b squared. Now plug in the value of b that we just found. What did we just find? We found it was 6/5. We're raising that to the 2nd power, so we get 25 times 36 over 25 times 25, or 12 times 25. 25 times 36, that's 900. 12 times 25, that is going to be 300, so A turns out nicely as well. It is 3. So our function, y equals f of x, is 3 times, I'll go ahead and use a decimal here, 1.2 to the x power. That is our unique exponential function in that form, written in this form. You can actually write it in other forms that we'll talk about in videos to come, involving the special number e. That is our answer for this question. What about symbolically representing how delta y depends on delta x? This is trickier than it is for linear functions, much trickier in fact. What did we talk about for linear functions? We want to figure out how does delta y depend on delta x. Remember that these symbols represent change in these quantities. Delta y is the change in the output. It's the new function value at the new input, which I write as x plus delta x, minus the old function value at the old input x. What is that going to be for this function? Well, when you plug x plus delta x into this formula, you need to replace the x with that expression there, x plus delta x. So we're going to get 3 times 1.2 to the x plus delta x power. Subtract what you get when you plug in x to the function, 3 times 1.2 to the x. And then you stare at that a bit, and you wonder, I wonder if I can simplify this at all. And it turns out you can. And with an exponential function like this, this will always work. You should look at this expression and say, there must be some rule of exponents that will allow me to change that. I hope you remember that. And yes, it is. Usually you do the algebra the other way. Here we're doing the algebra to separate this out into 2 different exponential terms, 1.2 to the x times 1.2 to the delta x. Delta x and delta y both represent one quantity. I still subtract 3 times 1.2 to the x. And then you look at that and say, can I do anything with that? Is there anything I can do to help me here? And both terms have a common factor of 3 times 1.2 to the x. It is worthwhile, it turns out, to factor that out. You can see this is more complicated. What's left on the inside? It would be 1.2 to the delta x power minus 1. So delta y depends on delta x in kind of a complicated way, and not only does it depend on delta x, it also depends on x itself. Is there any way to make sense out of this? Well, in the last minute or so here of this video, I want to start getting you thinking about the right way to make sense out of this. What I want you to do is I want you to think about the fraction delta y over f of x. In other words, f of x plus delta x minus f of x divided not by delta x as you might be thinking I was going to do, but instead dividing it by f of x. What's going to happen when you simplify that fraction? Something nice happens. The 3 times 1.2 to the x's, they go away, and you're left with something simpler. 1.2 to the delta x power minus 1. So even though delta y depends on both x and delta x, this ratio, delta y over the function value at the old input x, just depends on delta x. And in fact, if delta x is 1, you'd have 1.2 to the first power minus 1. 1.2 minus 1 is 0.2, illustrating the fact that we have 20% growth in this example each time x increases by 1 unit. Why is this fraction really representing the growth rate as a percentage? Not always when delta x is 1 for a generic delta x, but if we plug in delta x equals 1, that is representing the growth rate. Think about that before you watch the next video.